Partial fractions is a technique of integration that is important and we focus on in this video. Now first I want to just begin with these two rational functions and suppose we add them. Okay, so how would you add two functions like this? Well, we would get a common denominator, which is in this case is just the product of the two, x plus 1 and x minus 3. And then you would multiply this first term by x minus 3 over x minus 3. So this would be 2x minus 3. And then we have a minus 1. Maybe I'll put the 1. You would multiply the second term by x plus 1 over x plus 1. So we would have x plus 1. And then in my numerator, for example, I have 2x minus 6 minus x minus 1 over this, x plus 1, x minus 3. And then this is a x minus 7 over x plus 1, x minus 3. Okay, now partial fractions, so maybe I'll write this in blue, partial fractions goes the other way. Partial fractions goes the other way. And what do I mean by this? Well, suppose we wanted the integral of a function like this, x minus 7 over this product, x plus 1, x minus 3, minus 3 dx. Okay. Well, this is not something that we can, it's not a substitution. You could try to see if it's a substitution. Let's just check because we're talking about this for the first time. If you multiply through in the denominator, what is this rational function? It is, we have an x squared, we have minus 3x plus x, and this would be a minus 3x plus x, and then we have a minus 3. And as written, you don't see, we could think, and we have already, about having u in the denominator, but then in this case du would be 2x minus 2, and I don't have a multiple of that in my numerator, for example. If you try to break it into the sum of two integrals, as we've also practiced, well, in short, let me just say, I'm not sure how that would help me, okay? So my point of thinking about it this way was to say it's not an obvious substitution, looking at the function with the denominator multiplied out. But, well, we know how to integrate this function just because of the way it was handed to us. So in partial fractions, we're handed things that look like this as our integrand, and through the technique, which we will get to momentarily, we will find this number and this number. And so then, once we have that, then we would just, for example here, integrate. We would integrate 2 over x plus 1 minus 1 over x minus 3 dx, okay? Because these two are equal as functions, for example. We just got a common denominator to see these two are equal. And then through this technique, we will go the other way. That's my whole point. Now, how do I integrate something like this? Well, you could break it into a sum of two terms and do substitution on each one. But let's talk about what the substitution would be. This is another type for a term like this where you can just write it down without having to go through the steps. So what would, maybe at this point I will erase up here to think about this, because integrands that have pieces like this come up many times in this section. Okay, so I'll just erase that part. So what would the integral, we can pick either one of these terms of this. I'll just do this one because it's the first one, b. Well, if you wanted to go through all the steps, technically, as I mentioned, substitution, where u is x plus 1, du is dx, then, well, You see, du is dx, or you can also think the derivative of u is just 1. Whenever I see a substitution of this form, I won't go through all the steps. So let me show you what it is here. I will, and then from then on out, I won't. Okay, so here, well, this would be an integral 2 over u du. We integrate to ln, absolute value of u plus c. Then we go back to x. Okay. So anytime I have an inside function that has derivative 1, which will either be an x minus a constant or x plus a constant, I won't take the time to write out the steps of substitution. So back to this problem, here I would get 2 ln. This we actually did write the steps for, but this one, it's minus ln absolute value x minus 3, okay? Because it's the same idea, where if you wanted to work through the steps, u would be x minus 3 here, but the derivative of u is just 1, or du is dx, so it makes the substitution a lot simpler than usual. Okay, so we will see terms like this appearing. Well, okay, we found now the integral of this function, but typically, as I mentioned, we don't start with it already broken into pieces. It was just to think about what we're going to be doing here. Technique. We will integrate, so we have integrands, I will say, of the form as follows. P of x over q of x, where, let's see, where p of x and q of x are polynomials, and we need that the degree of the numerator p of x is strictly less than the degree of the denominator in order to do partial fractions. Strictly less than. And I will mention what we do when you have greater than or equal to for this degree, but partial fractions, the technique, we need the degree of the numerator less than degree of the denominator. Okay, so let's do an example where we actually start with something of the form polynomial divided by polynomial, and this will be the integral of 5x plus 5 over x squared minus x minus 6 dx. I think this is what I have. Yes, okay. Okay, well, the first thing we want to do, if we sort of get inspiration from the beginning example, is we would like to look at the denominator factored. So here, this is 5x plus 5 over, we factor this. We'll factor it as much as we can, and this factors into two linear terms. We have minus 3 and plus 2. And if you don't see it, you can check. Minus 3 times 2 gives us the minus 6, and if you add, you get minus 1, and so in fact this works. Now, we will have, just as we saw from the first example, that we had something, it was factored, of course we went the other way, but we had a constant over the first linear term, a constant over the second linear term, and this is what we do for partial fractions, except we don't know what the constants are. It's the whole technique, or most of it, the algebra of the technique, I will say, is solving for the constants. Okay, so what we want to do is we set 5x plus 5 over x minus 3, x plus 2 equal to, we have one constant over this linear term. We have another constant over this linear term. We need to find a and b. Once we do, we will just be able to integrate. This will be a log, this will be a log when we integrate, right? And then we have the answer, the antiderivative for this function. And the steps here are very much like the first example. Well, if these two are equal, what I want to do is get a common denominator, and then I will be able to set the numerators to be the same. Well, the common denominator, you already see it on this side. And so, let me come down here. This would be a, x plus 2, plus b, x minus 3 over this product. Okay, very much like this we did at the very, very beginning. And then maybe I'll do it in one more step. This is ax. Oh, I might need a little more space. This is ax plus 2a plus bx minus 3b all over this, x minus 3, x plus 2. Okay, at this point I might move up here to get some space. Well, now is when we have two rational functions, or you can think fractions, that are equal, and they have the exact same denominator. We may set, okay, maybe I will write it down here and then I will move. We can just set the numerators to be the same. So we must have 5x plus 5 is, and now let me just group some things over here. What I want to do is group everything with the x, and then group everything without the x, which would be 2a minus 3b. Okay, so now I have the two numerators equal. I just grouped the numerator on the right-hand side so that I have all the coefficients that have the x together, and then you can think about the coefficients that have the 1 together, okay? Now this equation must hold for all x. This leads to a system of two equations, because just looking at it, it looks like, well, I have one equation and I have two unknowns, a and b. How am I going to solve for that? Okay, but this is true for all x. This leads to two equations, and one of them, it says the coefficients in front of the x terms must be equal. So we get that 5 equals a plus b. Okay, that's working here. That the coefficients in front of the x must be the same. That's setting this equal to this. And then the second equation we get, well, the coefficients in front of the 1 must be the same. That this must equal this. Okay, and now the other part says that 5 equals 2a minus 3b. Okay, well now you have, there's a few ways you can do this. We do not have linear algebra as a prereq. In fact, I think this class is a prereq for linear algebra, but this is a very simple system of two equations and two unknowns. We don't get into anything too complicated here. I can just, for example, one thing I can do, you can always take a multiple of one equation, add it to the other. And here I see a minus 3 and I see just plus b. So I'm going to take 3 times this one and add. And then what will happen is I won't have any b's in my answer, right? This is 3b minus 3b, 0. Then I have 3a plus 2a is 5a. Then 15 plus 5 gives me 20. This allows me to solve for a. We see that a is 4. Once I have a, I pick my favorite of the two equations because they'll say the same thing. Maybe the top one then says 5 is 4 plus b, or b should be 1. Okay? You could also check here. This would say 5 is what? 8 minus 3b. Then you would add, you'd get minus 3 is minus 3b, like that, b is 1. So you can pick which one you put a into, and if you found a correctly, you'll get the same answer for b. Okay, so now what does this say? Well, what this says is that I can integrate, right? That I know what this integrand is in terms of a sum of these, oops, not minus 2, squared, in terms of these linear pieces as my denominators, which become logs when I integrate them. Okay, so this is equal to, well, I go back to here, a is 4, x minus 3, plus b is 1, dx, and now The integration part here, at least in this problem, is not bad. It's like the first thing we talked about. Ooh, except I don't want to leave off my 4. This is 4 ln absolute value x minus 3 plus ln absolute value x plus 2. Don't forget the plus c. Okay? So this is the antiderivative, or the set of all antiderivatives in definite integral for this problem, and this illustrates the technique of partial fractions. Let's talk a minute about the different kinds of terms you can have, because not all polynomials factor into distinct linear terms, and it's even the case that not all polynomials factor into well, take out the word distinct, just linear terms, right? Because you have some that are irreducible quadratics, for example. Okay. So now, let's just look at the kind of terms that you see, and we'll do several more examples. So if you see a p over x over q of x, and they're both polynomials, the degree of p of x strictly less than the degree q of x, okay, and these are both polynomials. I'll write this. And we want to do partial fractions. So what kind of terms can we see in q of x when it's factored completely, right, where you can't factor it anymore? Well, every term of the form, so if you see a term that's an ax plus b and it's distinct, this is distinct and linear. Well, we just saw that in the last example. When you do your partial fractions decomposition, you will have a term of the form capital A over ax plus b, like this. So this side, I would say, is in the decomposition. This is what you have a term. Or I should say factors of. This is better, and then there are terms if you think about the sum. So factors in q of x, and these are the terms in the decomposition. Okay, maybe that's a little more clear. Well, you could also have repeated linear like this. You could have an ax plus b. Okay, we'll say to the n. Do we really want to say to the n? Let's just do cubed, and we will see the example. Repeated linear. Well, I'll state it, and then I will state what it would be if you let it be n. Okay, we're not going to really see any that high above 3, because you have a lot. You have a constant for every single power, and I'll make that comment. Well, here you would have an a over ax plus b, and then you would have capital B over ax plus b squared, and then you would have capital C over ax plus b cubed, like this. If it was degree 4, you would have a d over ax plus b to the 4th, or you keep going, right? That's why I decided not to. I could state it in terms of n. I have a capital A1, capital A2, capital A3, etc. I just decided to state it in terms of 3. But one thing you will see is whatever the degree is, this is something of degree 3, if you multiply it all out, that's how many constants you will need to solve for in your partial fractions decomposition. Okay, so this is if you have repeated linear, and I will do an example of this also. But what else can you have? You could have an irreducible quadratic. And let's say distinct just for, I don't need to put it, oh, okay, it's fine. So this would be an ax squared plus bx plus c, but being irreducible, if you think about quadratic formula, it means that this b squared, I'll say where b squared minus 4ac is less than 0. So it doesn't factor over the real numbers. Then, well, as I mentioned, every whatever degree you have, that's how many things you have to solve for, how many constants you have to solve for. So this here, in your partial fractions decomposition, you would have a capital AX plus B over this irreducible quadratic, like this, okay? So we have degree 2. There are 2 coefficients we need to solve for. And then, for example, if you had a repeated irreducible quadratic, you would have an AX plus B over it. Then you'd have like a CX plus D over it squared. And then you'd have a EX plus F over it cubed, like this, into however many powers that you have. But, I mean, you can imagine the higher degree that you have in your denominator, the more coefficients you have to solve for. We're not going to be solving for some big 8x8 system of unknowns, not without the power of linear algebra, which we don't have. So I think this is a pretty good discussion so far of the types of terms you can see. And at this point, I would like to focus on doing some more examples. We see, looking at the integrand, certainly the degree of the denominator is bigger than the degree of the numerator, which is wonderful. And we can factor the denominator. So maybe I will do this up here. X squared plus 1. What's common to both terms is an x squared, and then we have an x minus 1. So this distinct linear, but the x squared, this is really repeated linear. I mean, if you wanted to match it up to how I wrote repeated linear, you could think about it this way, that x squared is 1x plus 0 squared, right? This is really a repeated linear. Okay, so maybe I will erase this comment. It was just a side comment. So what is the partial fractions decomposition when you have a repeated linear and one distinct linear? Well, we have a over x plus b over x squared plus c over x minus 1. Like this, we have this a over x plus b over x squared. Those two terms came from this being repeated linear. And then we have one distinct linear, and we have a c over x plus 1. Okay, this matches what we were just talking about over here. Well, just like in the first example we did, we want to get a common denominator. And now you have to be careful here. You don't multiply this by both of these, because the common denominator is just an x squared times x minus 1. So for instance, here on this first term, I will multiply by x times x minus 1, right? So maybe let's do that here. I will rewrite this side, x squared, x minus 1. This would be, we would have an a, we would have an x, x minus 1, okay, plus we have a b. Well, for the x squared here, all I need to multiply that term by is just x minus 1. And then for the c over x minus 1, this term I need to multiply by x squared. I have c x squared all over x squared, x minus 1. Now again, we would like to equate the numerators because these two are equal, same denominator. The numerators we set equal. Okay, so maybe I will do that in black just so we can have some division on the board of what's going on. Okay, but I will go ahead and multiply all this out. This is a x squared minus a x. Then I have plus b x minus b, and then I have plus c x squared. Okay, then as in the first, well, almost like it, except instead of just grouping stuff with x, grouping stuff with the 1, we have 3. We have an x squared. Well, I'll have to rewrite this side, or we have to at least think about it. But we see the terms x squared, x, and 1 would be what we separate by. So we have an x squared, then times x squared has a plus c. I'll do it like this, and then we can see. Okay. Then we have plus x. And this has what? Minus a plus b. Minus a plus b. And then we have a 1, which just has minus b right here. Okay? Now on this side, what is the coefficient in front of x? Well, it's just 0. So we have x squared plus 0x plus 1. And this will lead, you see this makes sense. I have 3 unknowns here. 3. It's hard to put down your pinky without moving the other ones. Okay, we have 3 unknowns, a, b, and c. We will have 3 equations to solve for the 3 unknowns. And the equations are a plus c is 1, minus a plus b equals 0, and minus b equals 1. Okay, well this is I think maybe even easier to solve as a system than our first one, because immediately we see b is -1. And then we go up to here. If b is -1, this is minus a minus 1 is 0. Okay, so we are also going to get minus a is 1. We will get a is -1. And now we have this. We have minus a. Oh, excuse me. A is -1. Minus 1 plus c is 1. We can just add. We get c equals 2. Okay, so now I'm trying to think where to go with this. Maybe I will erase part of this so I can write right underneath the integral. But you see, I have my coefficients through this technique, partial fractions. I have found a, b, and c, okay? Okay, so I will come up here. Maybe I will draw a line right here. And then I will have some space for my integral. So this here, this integral equals, well, I have a minus 1 over x. I have b minus 1 over x squared. And then I have plus c, oops, I almost wrote c, which is 2 over x minus 1 dx. Okay, all of this we can integrate. This is the beauty of partial fractions, okay? Well, this is negative ln absolute value of x. Now, if you need to remind yourself about this integral, I have room for a box over here. If we integrate, this is negative x to the -2. This is the second term, right? Well, we would add a power, divide by the higher power. Okay, well, negative, this is positive, and the -1 power, well, okay, plus c, very nice. This becomes a positive 1 over x plus c. Okay, so this was a little side box because the first and the third terms I can just do at this point without really writing much. But here's the work for this second term. So we have plus 1 over x, then we have plus 2 ln absolute value x minus 1 plus c, like this. So this is my indefinite integral. And this was an example of partial fractions where we had one of the linear terms was repeated. Here's another example. Again, just to check, to make sure we can do this one, you notice the degree of the denominator is 3. The degree of the numerator is 2, which is less than 3. So this is something that we are prepared to do partial fractions. Now, you might think that you still have some factoring to do, but if you look here at this term, b squared minus 4ac is 1 minus 4 times 4, which is negative. Well, it's negative 15, okay? So what this says is that this is irreducible. And this is our first example, at least so far, of having an irreducible quadratic term in our partial fractions. Okay, well, what does this mean? Well, it means, let's write out the form. We have a linear term, distinct. We have one irreducible quadratic. So my partial fractions is going to look like this. A over x plus bx plus c over x squared plus x plus 4, like this, okay? So now, okay, maybe I'll leave that. Now let us get a common denominator, right? Just like we've been doing. So let's get a common denominator. This part doesn't change too much. Maybe I'll go back to black. We're going to have, well, the a over x, we will multiply by this whole quadratic. So we will have a, x squared plus x plus 4. And then we're going to have an x, because this term over here, we multiply by x over x times, it'll be bx plus c. And this will be all over x times x squared plus x plus 4, like this. And then we can, maybe I'll multiply everything out while I'm still in this fraction part. It's going to be an ax squared plus ax plus 4a. Okay, then we have bx squared plus cx. Okay, now let me, well, finish writing. Okay, so now what we want to do, let's take this numerator and we set it equal to this numerator. Right? This is our whole goal here, and then we will solve for a, b, and c, just like we have done. Okay, well, 6x squared plus 5x plus 16. But let's go ahead and group everything with the x squared, group everything with the x, group everything with the 1. So this will equal x squared times what? Well, I have a plus b. And then I will have plus x times a plus c. And then I have plus 1 times 4a. Okay, just like this. Okay, we will have 3 equations, 3 unknowns, solve for a, b, and c. Okay, very nice. The 3 equations become that a plus b is 6. That a plus c, c, is 5, and that 4a is 16. Okay, immediately we solve for a. Divide by 4. We have a is 4. And then just from this, we get both of these. Because, for instance, 4 plus c is 5. C would be 1. And then here, 4 plus b is 6. B will be 2. Okay, so now we have our coefficients. So maybe just like the last one, I will erase here to give me some space for my integral. Okay. Now we integrate. This is equal to a is 4 over x plus, well, we have 2x plus 1 over x squared plus x plus 4 dx. Okay, now I will break this into 2 integrals just so that when I work on this term, it's clear. So I will write it like this, 2x plus 1 over x squared plus x plus 4 dx. Okay, well, this first one we know is 4 ln absolute value of x. This one, When you're integrating, as I mentioned the first day, first look and see, does a substitution jump out? Do you see an inside function and a multiple of its derivative? Here, the answer is yes. So I can write it up here. U is x squared plus x plus 4. My inside function is in my denominator, and I am not going to break this into a sum of more terms because here du is 2x plus 1 dx, right? I take the derivative of u. It's 2x plus 1, okay, plus 0, right? Well, look, handed to me in my integral is exactly du, okay? So this integral is going to be the integral of 1 over u du. So let's write that. Well, first of all, I can evaluate the first. This is 4 ln absolute value of x. And then this is an integral, 1 over u du. Okay, 4 ln absolute value of x plus. Here, normally I would integrate with respect to u, ln absolute value of u, go back to x, but I will just write it in terms of x in one step. It's 4 ln absolute value x squared plus x plus 4, and then plus c, like this, okay? So here is this indefinite integral where we had one distinct linear term and one distinct irreducible quadratic partial fractions. This one is a little different. Well, in fact, it's only one term. If you look at the denominator, this is irreducible quadratic. So here, b squared minus 4ac is, well, it's negative 36, right? Because b is 0. This certainly does not factor. So this is irreducible. And we only really have one term. But what I want to illustrate here is what you would do if you happen to have the degree of the numerator bigger than the degree of the denominator. So certainly this is a rational function, p of x over q of x, or p and q are polynomials, but the degree of the numerator is 4, the degree of the denominator is 2, okay? This type of partial fractions really will come up in future classes. So what would you do? Well, what you would do here, if the degree of p of x is bigger than or equal to the degree of q of x, the first step, if you have rational function and you have this situation, we must long divide. Now, this long division is not too terribly bad. Put the numerator, which is the larger degree polynomial, here. And then you put a divide sign. Out here, you put the, like this. Here's the denominator. So you're going to get some polynomial and a remainder. When do you know you're done? When the remainder has degree lower than 2. In this case, or whatever the degree here is, then you're finished. This one will be done in just one step, but in principle, you would have to do multiple steps, just like you divide numbers. Okay, so how do we long divide polynomials? You look at the highest terms, and if you need to, what do you multiply x squared by to get x to the 4th? Well, x squared, right? So we put the x squared here, and then we multiply and subtract. It's just like when you long divide numbers, but for many of us, including myself, it's been a long time since I've actually divided numbers this way. Okay, so here, multiply, we get x to the 4th. And then we multiply, we get 9x squared. And then subtract. So this is 0, 0, and then we just have x plus 2. But you notice, and this is what I said, I was not going to do a terribly involved long division, but you do notice here that this degree is strictly less than this degree, and so we are finished. This will be the remainder. Okay? So what this says for this function I've now long divided, this integral is the same thing as, oh, maybe I should go back to black. I can just write here, we have this equals the integral. Well, it's x squared plus, we have x plus 2 over x squared plus 9 dx. This is the part that we got, you know, the quotient. This is the remainder, so you put that over this thing, just like you would dividing numbers. This integrand, or this piece of it here, which is the x squared, of course, we know how to integrate. This piece is very much like something we did the first day, where we're going to break it into a sum of x over this plus 2 over this, okay? So here, this is equal to, here is x squared. Then we have x over x squared plus 9 plus 2 over x squared plus 9. And this is a good exercise because things of this form come up in partial fractions decomposition. Maybe I will come back here and compute some pieces. Then I will go and put them in, I will add the 3 pieces together. I'll do it like this. This, I think, is a reasonable way to organize my work. The first of the 3 pieces is the easiest, as I mentioned. Oops, I started to write the antiderivative. This is x cubed over 3. This one, substitution, okay? We see u is x squared plus 9, du is 2x dx. We have x dx, which is 1/2 du, okay? So this becomes the integral, it's 1 over u times 1/2 du, which is 1/2 ln, ln, absolute value of u, and then we go back to x. This is 1/2 ln absolute value x squared plus 9 plus c, okay? So now we have term number 1 here, term number 2, and the last one. This is one reason that I went over that in our substitution video. Remember, this was the tan inverse. Okay? If you have an x squared plus a squared in the denominator and you integrate, you have 1 over a tan inverse x over a, like this. In this case, a is 3. Of course, then we have a 2 in front, so this will be 2 over 3 tan inverse x over 3 plus c, like this. This would be an antiderivative for this. If you wanted to, you can go through the steps again that we did. We did it for x squared plus 4, but we would get this exact antiderivative. Well, now let's just put this all together. So my final answer, we add them all up. Oops, don't want to forget the half. ln absolute value x squared plus 9. This is one that you could, without a doubt, put open parentheses instead of absolute values because x squared plus 9 is always positive. You're also fine to just leave them there. You don't have to think if what's inside is positive or not. My plus c had to be moved to another line, but it's there. Don't forget plus c. So here is my antiderivative in this case for this rational function where we had to first long divide. Okay. What we see here, we have a distinct linear, and then here, this is an x squared plus 1, and just like the x squared plus 9, this is irreducible, okay? So we cannot factor the denominator anymore. So we're going to look for partial fractions of the form. Okay, but maybe before I start that, we see here, for instance, unlike the last problem where we had to long divide, my denominator has degree 3 and my numerator has degree 2. So we are in good shape. The degree of the numerator is strictly less than the degree of the denominator. Okay, now we will get back to what I was saying. The partial fractions form will be like this. Okay? A over x plus 3 plus bx plus c over x squared plus 1. This is the form. Okay, now we will get a common denominator, which involves, well, as we know, this one gets multiplied by x squared plus 1 over x squared plus 1. We're going to have a x squared plus 1 plus, then we have bx plus c. This one's multiplied by x plus 3 over x plus 3. Oh, wait. Oh, we're okay. Uh-oh, I'm stuck. Wasn't sure I started recording again. Okay. So we have x plus 3 divided by, and the common denominator is here, x squared plus 1, like this. Okay. Well, then we can multiply everything out. For instance, what do we have? Ax squared plus a, and now I need to distribute all of this. Just be careful. This is where I make all my mistakes. Okay, so we have a b. Oh, see, I already made one. This is supposed to be a plus. I put equals. Well, the funny thing is I said be careful, and I already had put equals instead of plus. In any case, here we go. We have bx squared. That's first. The outer is a 3bx. Inner is a cx. And last is a 3c. Okay, let's hope that's right. We will find out, right? Okay. Then the denominator is x plus 3, x squared plus 1. Okay, so let me go ahead and work with this numerator, set it equal to the numerator on that side, and I will group everything in one step. So this numerator is 2x squared plus 3x plus 11. We set this equal to everything with x squared. We have a plus b. Okay, everything with the x, we have 3b plus c. Okay, everything with a 1, we have a plus 3c. Okay. Now let's make sure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. At least I have this right number of terms. I didn't leave anything off. Now we have a system. Should be 3 equations, 3 unknowns, because we have unknowns a, b, and c. And the equations are, well, we set everything in front of the x squared. So a plus b is 2. Then everything in front of the x will be 3b. Oh, maybe I will space this out some. We have 3b plus c is 3. And then everything in front of the 1, we have a plus 3c equals 11. Well, this one, we don't initially have where we can just solve for one of them, right? So we're going to have to do something to solve. Now, what are some things we can do? Well, for example, I see an a and I see an a. I could take, for instance, this equation minus this one. I will have no a's, so that would be a second equation that involves b and c. And then I could use also this equation that involves b and c. Those would be 2 equations, 2 unknowns. I solve for b and c. And then once I have, well, either one of them, I can get a. So this is my strategy. So what I said I would do is I'm going to take this equation and this equation, but I'm going to take, oh, maybe I shouldn't star them. I will take minus this equation and add it to this one. And then I will get Maybe I'll write it below when I do that because I can go down. Okay, very nice. This will work this way. Trying to be as clear as possible. I get a minus a. Then I have minus b. I have plus 3c. This will be 11 minus 2, which is 9. Okay, now I will recopy because this is what I said I wanted to get to. I have this equation of b and c, this equation of b and c. Let's find b and c. Okay, so we have 3b plus c is 3, and minus b plus 3c is 9. Okay, well, you can do a number of things. Maybe I will just multiply, because I see a negative, I'll multiply this one by 3 and add. And I wind up getting, this adds to 0. This is 1 plus 9. We have 10c equals, this is 27 plus 3 gives me 30. So c gives me 3, or equals 3, I should say. And then we can go back to either one of these. C is 3. Maybe I will put it in a box here. And we get 3b. Let's use the first one. We have 3b plus 3 is 3. Well, this says that 3b is 0, or b is 0. We found b. And finally, well, the easiest one to go is the very first equation. Here, because if b is 0, this gives us that a plus 0 is 2, or a is 2. I'll box it in black, and then I will, oh, not 0, 2. Okay, so what I did, this equation here came from this first one. I just substituted b equals 0. But I could have also gone here. A plus 3c is 11. I could have put in 3. That would say a plus 9 is 11. Subtract 2, and I would get a equals 2 like this also. So you have different ways of solving when you have 3 equations, 3 unknowns. Okay. You might do it different than your neighbor and still get the same A, B, and C, and that's perfectly fine. Okay, well now I have solved for my constants. I'm ready to integrate. The integral, well here, A is 2. B is 0, so I have a 0x plus C is 3. Okay, well, we can simplify. This is 2 over x plus 3 plus, this is just 3 over x squared plus 1 dx. Here we don't need any substitution or anything like this. The first integrand is a log. Well, I guess technically it's substitution, but as I mentioned at the beginning of this video, I won't write it if the derivative of the inside function is 1. But we don't need any substitution on the second term. We have the tan inverse. So this is 2 ln absolute value x plus 3, the tan inverse of x plus c. And here is the antiderivative, or the indefinite integral for this function here. Okay. Let's do one more example. This is going to look complicated, but here's the instructions. We would like to find the general form of a partial fractions decomposition. What I mean by this is we're not going to solve for the coefficients. So in other words, do not solve for a B, C, etc. And you will see when I write it that we wouldn't want to. At least just using markers and standing up here at the board. Okay, so let's write something. I can put really anything up here because the numerator I need to make sure it has smaller degree than my denominator. So now we'll make sure I put something up more than degree 4. Let's do x squared plus 4 squared. We'll do x minus 2 cubed. And then we'll have an x plus 11. Okay, dx. I think that looks good. Well, what is our degree of our denominator? Well, here, this term has degree 4. Then we have plus 3 plus 1. This is degree 8. We will write out, and this involves just understanding the statement of what the terms look like, the general form of the partial fractions decomposition. But if you imagine, we will have, because this is degree 8, we will have 8 coefficients, and we would have 8 unknowns. It would turn into a system if we set it equal to the numerator. Well, if we went through the steps, I should say, where we get a common denominator, set the numerators equal, we would have 8 equations, 8 unknowns. And I don't know about you, but me personally, I wouldn't be doing that at the board. Not without mistakes, and not without taking way too long for this video. So we really just want to practice the form. 8 would be way too many for us to solve in this class. Okay, so here we go. The first term, repeated irreducible quadratic. So we have an ax plus b over the irreducible quadratic. But, and I mentioned this, but I didn't write it, we would also have, here, we would have a cx plus d over the irreducible quadratic squared. And you can count even now before we do any more. You see, corresponding to this term here, we have 1, 2, 3, 4 unknowns, which makes sense because this is a degree 4 term. Okay, whatever term you have or whatever degree you have in the denominator, that many coefficients. Okay, now we have repeated linear. It's repeated 3 times, so we're going to have, well, I've got to move to e over x minus 2 plus f over x minus 2 squared plus g over x minus 2 cubed. Okay, those 3 terms correspond to this here because it's repeated 3 times. And then finally we have a distinct linear, so we have an h over x plus 11. And you can count, we have 1, 2, 3, 4, 5, 6, 7, 8 coefficients here. And it makes sense, as I mentioned, because the degree here in the denominator is 8. Okay.